All right, so let's do part 2 on rational functions. We're on number 14. So it says find the x and y intercepts for each of the graphs of the following rational functions. So when we're doing graphing, or when we're graphing rational functions, and it's really true when we're doing any kind of graph, finding x and y intercepts are usually pretty good points to find, especially the y-intercept is usually quite easy to find. So we're just going to practice finding intercepts here. So I usually find the y-intercept first just because it's normally the easier one. So for the y-intercept on the first one, I want to let x be 0. That's how I find a y-intercept. So let's find f of 0. So that's 1 over 0 plus 4, which is a fourth. To find the x-intercept, actually, so the y-intercept is 0, 1/4. To find the x-intercept, remember f of x is just another name for y. So we're going to have 0 equals 1 over x plus 4. So to solve this equation, I'm going to go ahead and multiply by the LCD here, x plus 4. On the left, we're going to get 0. And on the right, notice the x plus 4's cancel, and we get 1. Now that's a false statement, which would indicate there is no solution to this, and so there isn't going to be an x-intercept. Now I want to point out something here. The only way that this fraction, 1 over x plus 4, can equal 0 is if the numerator is 0. Well, the numerator is 1, it's never going to be 0. So really, just remember a fraction can only equal 0 when the numerator is 0. So really all you have to do when you're finding an x-intercept in a situation like this is figure out when your numerator is equal to 0. All right, let's move on to number 15. So for the y-intercept, we'll plug in 0 for the function, and notice you're going to end up with negative 3 over 2. 0 minus 3 is negative 3, and 0 plus 2 is 2. And so our y-intercept is 0, negative 3 halves. What about the x-intercept? Well, if we let y be 0, we get 0 is equal to 2x minus 3 over x plus 2. Now again, what I was just saying a minute ago is this fraction will only equal 0 if the numerator is 0. And so all we really have to do is set 2x minus 3 equal to 0. And when we solve that, we get 3 halves. And so we chose y to be 0, and we got x as 3 halves. Our x-intercept is 3 halves comma 0. Now I'm not going to go through 16 in detail, but you may want to try it and then you can watch the video. So when you plug in 0, you should get 0. And so your y-intercept is 0, 0. Now when you find, so notice that's also an x-intercept. But it is possible there could be other x-intercepts, so let's go ahead and see what happens here if we let y be 0. Well, remember this fraction can only equal 0 if the numerator is 0. So I'll set the numerator equal to 0, and you see we get x is 0, which tells us we're not getting any other x-intercepts. All right, so now we're ready to start doing some graphing. So it says here, when graphing rational functions, it's important to make sure that the function is simplified when looking for vertical asymptotes. What if it's not simplified? In such cases, we will have a hole in the graph. Consider the following problem. For the given rational function, find any asymptotes and or holes for the graph, then graph the function. So here we have f of x equals x minus 2 over the quantity x squared minus 4. So notice first of all that the denominator factors here. But before, and we do have a common factor, but before we cancel our common factors, I just want to point out the original function has x squared minus 4 in it, and so our restricted values will be 2 and negative 2. So let's simplify now, and we get f of x equals 1 over x plus 2. Now when you graph f of x equals 1 over x plus 2, x equals negative 2 is also a restricted value. But what about the x equals 2, or the fact that x can't be 2? That's where we're going to have our hole. So let's move on, and I'll show you how this works. So let's go ahead and graph f of x equals 1 over x plus 2. We need to find our vertical and horizontal asymptotes first. So let's do that. So at our restricted value, we'll have a vertical asymptote. As far as horizontal asymptotes are concerned, notice that we're bottom heavy here. The degree in the denominator is greater than it is in the numerator. And so that's the case, that was case 1, where the asymptote will be y equals 0. So next, let's find a couple of easy points. Well, we talked about intercepts. So let's find the y-intercept. If you let x be 0, or you find f of 0, you're going to get a half here. So the y-intercept is 0, a half. What about the x-intercept? Well, if we let y be 0, notice our numerator is 1. And so this fraction's never going to equal 0 because the numerator will never be 0. And so there isn't an x-intercept. And so let's go ahead and graph what we have. We've got x equals negative 2 as a vertical asymptote. We have y equals 0 as a horizontal asymptote. And we have 1 point at 0, a half. And so in order to graph this, we're going to need to find a few more points. Now on the right side, and basically what ends up happening is we really need to look in each region that's separated by any vertical asymptotes. So here, let's see what's going on the right side of x equals negative 2 first. So what I'd like to do is maybe figure out what's going on when x is negative 1. So I'm going to make a table of values, and if you let x equal negative 1, now you can either plug it into the function and do the computation by hand, or this is something where you can plug in the function into your calculator and use your table of values to get a few points. Now I'm making a video and it'll show you how to do that if you don't know how. But anyway, in any case, you should get, oh, and actually the other two values, notice we want to know what's going on this side of the asymptote. And so negative 3 and negative 4 would be some good values to find. And so what you should get when you do those calculations is 1, negative 1, and negative 1/2. So notice when x is negative 1, we're at 1. Now as we go to the right, we know that the graph's going to approach the horizontal asymptote, and so it's going to look something like that. As we take this arc to the left here, it's got nowhere to go. It's starting to rise. It can't go through the vertical asymptote. The only thing it can do is get closer and closer. Now let's plot the points on the other side. We've got these 2 points here. So again, as the graph, we know as it approaches, I should say on the ends, it's going to approach the horizontal asymptote. So it's going to look like that. On the right here, it's got nowhere to go but down, and so it's going to look like that. Now, don't forget, we said we had a hole at x equals 2. See, the thing is, this function's undefined if x equals 2. And so our graph should not have a point at x equals 2. We need to put a hole in there. I think in the homework you have a couple of these, so you just have to watch out for a situation where the numerator or denominator can be factored, or both, and it turns out you have common factors that cancel. That's the case where you're going to have a hole. All right, let's move on to, I'm going to do a few examples of some graphs that don't have holes. So here's the process we're going to go through. It says graphing rational functions. For each of the following rational functions, find any vertical, horizontal, or oblique asymptotes. So find asymptotes. Then B, we're going to find intercepts, X and Y intercepts. And then C, we'll find a few other points. So basically we're looking to, in the regions separated by the vertical asymptotes. And then finally we'll draw the graph. So on number 18, the first thing I notice here is x can't be -1. That's my restricted value. And so for part A, my horizontal asymptote is going to be at x equals -1. As far as my horizontal asymptote is concerned, this is the balanced case where the numerator and denominator have the same degree. So we'll just use the coefficients here, y equals 1 over 1, which would be 1. And then anytime we have a horizontal asymptote, we're not going to have an oblique one. That only occurs when our numerator has the bigger degree. All right, let's move on to part B and find the y-intercept. So we need to find f of 0. Well, when we plug in 0 here, we're going to get -2. And so 0, -2 is our y-intercept. And let's find the x-intercept next. We want to let y be 0, so we'll get 0 is equal to x minus 2 over the quantity x plus 1. And again, this fraction here can only equal 0 if the numerator is 0. So let's set x minus 2 equal to 0. We're going to get x is 2. And so our x-intercept is 2, 0. And so now we're ready to start doing the graph. And we'll need to find a few points though. So I'm going to go ahead and put in our vertical asymptote and our horizontal asymptote. I'm going to plot the two intercepts we just found. Now notice, basically what you find is you really just need 1 or 2 points when you're to the right, or I should say on the ends. When you only have one vertical asymptote, basically what you're going to end up with usually is arcs on each side. And so we have those 2 points on the right here that would indicate what our arc's going to look like. We know as we go to the right, we're going to approach the horizontal asymptote. And going back to the left now, we can't cross the vertical asymptote. So the only thing that we could possibly do is just approach it or get closer and closer. All right, so it looks like we need to find a couple of points here. I'd like to know what's going on when x is -3 and -2. Really, we could use any x values over here that we want. I usually try to keep it simple and use the first couple that we see. All right, so if, again, I wouldn't, for somebody that's going on to calculus, you ought to be able to find f of -2 and f of -3 by hand. And it's good practice to do that. But when you get to the homework, you're going to do quite a few of these. So I certainly feel like it's reasonable to allow you to use your calculator. The main thing you want to watch for when you're putting these functions into the calculator is that you put your numerator and denominator in parentheses. And so, again, I will make a video for using the calculator, but that's the main thing you have to watch out for. So anyway, when you plug in -2 and -3, you should get 4 and 2.5. So let me go ahead and plot those points so you can see where the arc is. Now the arc could have been down here. We don't know. It would either be down below or up above. And by finding these 2 points, we know it's going to be up here. And so our graph's going to look something like that. All right, let's move on to the next example. So on this problem here, I'm going to want to factor the denominator first. I would use the AC method, or that's the way we've been doing it in our class. And you would get x minus 3 times x plus 1, which tells me our restricted values are 3 and -1. And of course, those tell us where our vertical asymptotes are. Now don't forget, your vertical asymptotes our equations, you should always write them separated as two equations. So x equals 3 and x equals 1 here. The horizontal asymptote, let's see, this is the case, this is case 1 where we're bottom heavy and our asymptote is y equals 0. Since this, we're not going to have a oblique asymptote since we don't have a bigger degree in the numerator. All right, let's move on to B. And so for the y-intercept, f of 0, well, let's see, that's going to be -1 over -3 here, which is a third. And so 0, a third, is our y-intercept. Let's see if there's any x-intercepts. So when we let y be 0, notice our numerator, if we set that equal to 0, we get x equals 1. So we do have an x-intercept at 1, 0. Again, all we have to do is set our numerator equal to 0 to determine if this fraction, or when this fraction would equal 0. Okay, so now we're ready to put in our asymptotes. I put in the vertical asymptotes here first. We've got also y equals 0 as a horizontal asymptote. Let's plug in our two intercepts. So remember, I told you earlier, a graph will never cross a vertical asymptote, but it is possible that it could cross a horizontal asymptote. In fact, this point right here is on the horizontal asymptote. Now there's a few possibilities here, looking at what we see here. This graph could go like this, or maybe something like this. Now, depending on what we find, it's also possible to get graphs that might look like this or something like this. So there's a number of possibilities when you have points between two vertical asymptotes. So normally you need to find more than just 2 points, or 1 or 2 points. So I'm looking at 2 here, and I'm thinking I'd kind of like to know what's going on when x is 2. So I'm going to go ahead and plug in 2, and you get -1/3. And so that's enough to tell me that the graph's going to look something like that. Now, if you had any doubts, you could always go to your table of values and find a few more points, but that is the way the graph's going to look. All right, so I'd also like to find out what's going on over here and what's going on over here. So let's pick some x values, -3 and -2, 4 and 5. And so again, I'm going to, you can do this by hand or you can do this on your calculator, but you should get these values here. And so let's go ahead and plot these 2 points when x is -2 and -3. And you can see our arc is going to be, well, let's see, as we go to the ends, we're going to approach the horizontal asymptote. Actually, the arc's going to look something like that. And this is what tends to happen, particularly on the outside of a graph when you're graphing a rational function. Now, you do find that there's a lot of variety with graphs when you're graphing rational functions, but this is probably more often the case than not, that you're going to have these arcs on the outside of any vertical asymptotes. All right, let's see what's happening when x is 4 and 5. You can see that our graph's going to look something like that. All right, let's move on to number 20. All right, so first of all, x can't be -1. And so we know our vertical asymptote will be at x equals -1. For horizontal asymptotes, notice there won't be one because here we're top heavy. And so this is the case where we have an oblique asymptote. In fact, we've already done the division that you would need to do here. That was problem 12. And we found that the oblique asymptote is at y equals x minus 5. Let's move on to the intercepts. So f of 0, if you plug 0 in, you're going to get 3 over 1, or 3. So we have 0, 3 as as a y-intercept. And then for the x-intercept, if we let y be 0, we get x squared minus 0 equals x squared minus 4x plus 3 over x plus 1. So again, this fraction here will equal 0 when the numerator is 0. So let's set our numerator equal to 0. And when you factor this, you end up getting x is 3 and 1. And so we're going to have x-intercepts at 3, 0 and 1, 0. All right, so let's go ahead and put in our asymptotes and the points that we found so far. So we have a vertical asymptote at x equals -1. Remember, we don't have a horizontal asymptote. So, but the vertical or the oblique asymptote, we have to graph the line y equals x minus 5. So we'll start at our y-intercept, which is at -5. And our slope is 1, which would be 1 over 1. So I'll rise 1 and run 1. And we end up here. So if you graph that line, it's going to look like this. And that's our oblique asymptote, y equals x minus 5. And then we have a couple of points here. Now it looks like it probably goes something like, something along these lines, something like that. So we might want to find out when x equals 2. You could even plug in some x values like 4 or 5. I'm just going to plug in 2 here. And when you do that, you're at -1/3. And so it looks like the graph's going to look something like that. Again, as far as end behavior is concerned, we know that we're going to approach the oblique asymptote on the end. Now it is possible sometimes a graph will do something like this, and so that is something that you could run into. So you might want to find a few more points here, like when x is 6 or 7, but for our purposes this will be good enough. And so now we want to know what's going on over here, and so I'm going to actually find 3 values here when x is -2, -3, and -4. And again, when you plug those values in, you're going to get these 3 values here. And so it looks like I need to extend my graph a little bit here, so let me do that. So at -2, we're at -15, -3, we're at -12, and -4, we're at -11.7. So again, I've got enough here that would indicate the graph's going to look something like that. All right, so let's move on to number 21. This is an application problem. It says the medical dosage, well, we have this function here, this rational function, n of t equals 0.8t plus 1,000 over the quantity 5t plus 4. Where t is greater or equal to 15. This gives the body concentration, which we're calling n of t, in parts per million of a certain dosage of medication after time t in hours. So first of all, it says find the horizontal asymptote of the graph and complete the following. Well, to find the horizontal asymptote, we look at the degrees, and they're both 1. So this is the balanced case, and so it's going to be, we find it's going to be 0.8 over 5, and that's 0.16. So that's going to be our horizontal asymptote. So if you look at the graph, you might possibly think that it's going to approach 0, but knowing what we know about finding horizontal asymptotes, we know it actually is going to approach 0.16. So let's look at what's going on here. It says n of t approaches some value or something as t approaches infinity. Well, this was supposed to be a t here. I messed that up. But as the time gets bigger and bigger, what's happening to n of t? Well, it's approaching 0.16, our asymptote. So let me go ahead and let's look at the graph a little more closely. I do have a typo here I need to fix. That should be meaning. So down below we have our asymptote at y equals 0.16, horizontal asymptote. And again, this is the t-axis, and that gives us time in hours. So as time grows, notice the graph's going down. And the y values give us the concentration. That's our vertical axis is measuring concentration. Those are our y values. So basically what this is saying is the horizontal, it says explain the meaning of the answer to part A in terms of the application. So what's going on here? The horizontal asymptote indicates that over time the concentration of the medicine will approach 0.16 parts per million. So really what's happening here is we're always going to have some of this medication in us. It's never going to be completely gone. So let me go ahead and write that. In other words, there will always be some of the drug in your body. It's what we sometimes call a trace amount. All right, and so that's the end of this video.